Welcome to the Church of Perpetual Life. We're live streaming, live in person, and live Zooming. And we're ready to go. My name is Neil Vandry, and I am your officiator. Terry, come on up. I'm your officiator tonight, so who's here for the very first time? For the very, very first time, put your hand in the air. All right. Very good. Lovely to see you all. I'm so glad you're here. And we have a special gift for you. We have a book, a very special and quite valuable book from Alcor, Saving Minds. Well, let me see that blue book. Well, we'll get that to you there. And we have some... There we go. Go ahead, Doug.
By the hand and let's build a better world.
Yes, that's fine.
We are one big family and we are the human race.
A proper greeting, if you will.
Big and beautiful
And we have a gift for you, and it's not just a little necklace, but we actually have a book and a pair of sunglasses. Not that you need the sunglasses at the moment, but the book I think you'll enjoy. That, of course, is Elaine Silver, who was here in concert last month. How many people missed the concert last month because you didn't come for the Halloween party? Missed. Oh, my goodness. So this is a replay of Elaine Silver. All right. Janice Books. Books. And sunglasses, if you have them. Yay.
Do unto each other is a wise and golden rule.
Every new person gets a free book and sunglasses. Okay.
And life is one big school.
For those of you who don't have a book, let me have one of those. That's it. Preserving Minds, Saving Lives. The best cryonics writing from the Alcor Life Extension Foundation. If you didn't get one and you would like one, we have them at our tables there. I think they're $8 or $10 or something. So that's on the honor system over there if you want to get one. They are Preserving Minds and Saving Lives.
We are building a better world. We are building a better world. We are building a better world.
So this party is pre-Thanksgiving, our Thanksgiving, our 11th anniversary. 11 years. 11 years building an immortalist, cryonicist, living forever, living healthy community. So you saw online, we've got many people Zooming from as far away as California. Actually, there are people who are also live streaming in the YouTube who could be as far away as Russia, England, Australia, all over the place. I don't know where they are exactly because they haven't checked in with me yet. But if you are ever away and you want to be here, all you need to do is get on your computer and say, hello there. And there's a whole community that kind of popped up during COVID. When COVID came, we had a writer that was going to come to speak. And by the way, he contacted me. He wants to come back in the spring. And he will be coming back. He wrote a book, great book on age reversal, and he's coming here in the spring. And he'll be doing a book signing and all of that. So after COVID, we went into Zoom world. We went into find members all over the place. And so it's so great to be here and with you. Who drove as far away as Sarasota? Okay, Bruce. Anybody farther than, that's about 4-hour drive. I know somebody comes, how far did you come? Manhattan. Flew down from Manhattan. Yes, yes. Washington Heights, I believe. Yes. Teddy's from Washington Heights, Manhattan. And that's, I guess you get the prize for being here from the furthest distance in person. But we've got Toronto. Where's Toronto? Oh, Toronto's got to be further, right? There you go. That's a whole other country. That's like a whole different country over there. Thanks for coming over here. Mira. Okay. So now what I'd like to do, we've had a kind of would you say we've had a little bit of a contentious election? I'm not going to get political. We had a transhumanist running for president come here, and I didn't get political then. And I won't get political now, but I will say there was a great divide. And I know looking among you, we have Democrats here, we have Republicans here, we have libertarians here. And it's time that we unite and become the United States of immortality, the United States of America and Toronto. Right? You know, the forefathers were thinking about annexing Toronto and Mexico, and it didn't happen. Maybe it would have been better, but maybe you don't think so. That's okay, that's okay. Summers, I used to go to Niagara on the Lake all the time. We'll talk. But here we're going to do a gratitude, grateful Thanksgiving. This is our Thanksgiving, and we give thanks. I give thanks for being here. I give thanks that I have a wonderful family here, my immortalist family. I give thanks for my boat that's now named Hurricane Luck. Hurricane Luck was a book I read when I was in the 5th grade about a little boy who went to the island, found a shell, Genoa volute, worth a lot of money to the little boy at that time. And I give thanks for the fact that I could come here during the hurricane and get away from some of that stress on the other coast. You got the sunrise, which I watched the other morning, and we got the sunset. I'm so much happier with the sunrise because I personally never want to see myself into the sunset. And for the cryonicists, that means the doer. And if I ever go in the doer, I expect and hope that you'll bring me out. Now, I've said to you a number of times that I will be having my 123rd birthday here. Has anyone heard that I'll be celebrating my 123rd birthday here? Okay. Leo, hi. I look great. Thank you very much. Thank you. Okay. Was that Bruce? Whoa. But you are all invited. And I sincerely mean that. I have faith in humanity and the Creator that we will have this opportunity in our lifetime right here, right now, right today. It's happening as we see it. A year ago, we had Ray Kurzweil, the most accurate predictor of the future, say that the singularity is nearer. The singularity? Anybody not know what the singularity is? It's okay not to. It's okay. We have a book out here that he gave away, and you can perhaps still get, that the singularity is nearer. For those of you interested in what that means, talk to me after the service. I'm happy to share what I know about that. Ladies and gentlemen, the volunteer of the month is Dr. Howard, and Dr. Howard has something to say as well.
Thankful and grateful to be alive today. Things that I have been given every day, including, of course, today, and to be able to share them and to be a blessing to others. To me, that's the most important thing.
Let's keep this as a unifying thankfulness and hopefulness.
So anyway, this is our creed. This is our mission. And I would like you all to read it along with me. Perpetual Life Creed. We believe that all of life is sacred and that we have been given this one life to make unlimited. We believe in our Creator's divine plan for all of humanity to have infinite lifespans in perfect health and eternal joy, rendering death to be optional. By following our gospel, we achieve eternal life, creating a heaven here on earth. We follow Nikolai Fedorov, who taught that the transcendence of the Creator will only be solved when humanity, in our unified efforts, become an instrument of universal resuscitation, when the divine word becomes our divine action. And we also follow Arthur C. Clarke, who said, the only way to discover the limits of the possible is to go beyond them into the impossible. And so we enter each day energized in spirit and empowered by the words of our prophets to live in joy, serving our Creator and all of mankind forever and ever. And I want to just also read a little peaceful, thankful thought. I am thankful for my many blessings. I count my blessings every day, from the smallest gifts to the ones that make my heart sing. I value them all and appreciate the uniqueness of each one. I am grateful for my family and friends, for people who support me no matter what, and I appreciate my environment, the beauty of the dawning sun, the breeze in my face, the birds that sing outside my window. And I add to my gratitude list, as I add to my gratitude list, my heart expands. Giving thanks opens the way to abundant blessings of healing, prosperity, and harmony. As I think of my blessings and give thanks for them, I deepen in joy and appreciation for my life. The bounty and beauty of the world around me magnify and multiply blessing by blessing, and therefore I am grateful.
Thank you, Peter. I'd like to bring up another segment that's new, and that's with Terry, who's going to lead us in a guided meditation for a couple of minutes. Come on. Has anyone meditated before in a guided meditation? Lovely.
Hi there, I'm Terry, and I'm so thrilled to be here to be able to share this with you. If you could all just close your eyes and get your hands in a comfortable position, either on your lap or wherever you want them. And what we're going to do first is we're going to do some breath work. So while your eyes are closed, I want you to take a deep breath in through your nose. Hold it for a second. And exhale through your mouth. Again, inhale. Hold. And exhale. One more time. Inhale. Hold. And exhale. Keeping your eyes closed, we're now just going to breathe gently in and out through your nose. And all I want you to focus on is the air going in and out through your nose. And what you're going to do is whenever a thought comes into your mind, visualize it just blowing away like the clouds in the sky. So just gently breathing in and out. I want you to relax your forehead. Relax your eyes. Relax your mouth. Relax your shoulders. Relax your arms and your hands. Gently breathing in and out. Relax your chest, your torso, your hips. Visualize the stress going down your legs and out through your toes. And you're completely relaxed, focusing on the air going in and out through your nose. Take another deep breath in. Hold. Exhale out. Hands in prayer. May the divine in me honor the divine in all of you. Namaste. Thank you.
Our speaker tonight has his own Wikipedia page, which I aspire to have someday. Antonei B Csoka, Professor, Doctor. I've been calling you a lot of things today, but he said I can just call him Anthony, and I appreciate that. He's a biogerontologist at Howard University who works on the molecular biology of aging, regenerative medicine, and epigenetics. Dr. Csoka has earned a bachelor's degree at Newcastle University in genetics. He has a master's in molecular pathology from the University of Leicester and a PhD in cellular and molecular biology from the University of Debrecen. He was a member of the consortium that identified the Lamin A gene as the cause of the accelerated aging disease Hutchinson-Gilford Progeria Syndrome, and participated in the first National Institute of Health Progeria Research Foundation workshop. He also showed that progeria is a true representation of aging with respect to cellular signaling pathways and truly recapitulates the normal aging process at the cellular level. He currently researches the molecular etiology of aging at the level of signaling pathways. He has authored and co-authored over 50 scientific papers. Many of you know that Dr. Csoka is a proponent of life extension, cryonics, and transhumanism, and has been identified as one of the top 20 socially connected professors on Twitter. He is a scientific advisor to the Alcor Life Extension Foundation, the UK Cryonics and Cryopreservation Research Network, and the Lifeboat Foundation. How many people have heard about the Lifeboat Foundation? Check it out, check it out. It's really worth it. It's so cool. And a fellow of the Global Healthspan Policy Institute, and was featured in the first Immortality Institute film, Exploring Life Extension from 2005, produced by Bruce Klein. Let's welcome our good friend, Professor Dr. Antonei Benjamin Csoka.
So, yeah, thank you, everyone. Thank you, Neil. Thank you, Bill. Thank you, Janice. Really excited to be here. I'm going to be talking about different aspects of aging, beginning with the biology of progeria and then going into aging itself. And then in the latter part of the talk, I'll be going into like more of a deep dive into the philosophical aspects of aging. And it was kind of a nice coincidence. I didn't realize that you had Nikolai Fyodorov in your creed. I wasn't aware of that, and I will be talking about him and his philosophy towards the end of the talk. So as I said, it's divided into three sections, this talk. The first part is about my sort of the way I got into aging, studying it. And that, for me, that was through studying progeria. That was my entry point. And then that took me to cellular senescence, which I believe is what I call the causal nexus of aging. I'll explain what I mean by that. And then I'll segue into sort of broader aspects of aging, the theoretical aspects, which I believe strengthen the fact that progeria is truly aging. I'll talk about something called the Weissman barrier. I'll explain why I believe aging is what I call a meta-disease. So there's that sort of dilemma that you're probably aware of. Do we call aging a disease or not? I believe there's a solution to that by viewing it as a meta-disease. And then I'll delve briefly into what I think we can do about it currently. And then in the third part, I'll go into the philosophical implications, as I mentioned, touching on the simulation hypothesis and how that applies to our current situation. And also Fyodorov, Nikolai Fyodorov, and his hypothesis of the common task, or his directive of the common task, and how we can sort of merge the simulation hypothesis and the common task into like a broader mandate, perhaps. So first of all, this part one, my personal story of studying aging. So when I got into studying progeria, there was an idea around that can be put as a question, like, has nature given us clues as to what was causing aging? This was like the late 90s, early 2000s. So the idea was, can we learn something about aging from studying progeria and related disorders. And there's actually a whole class of diseases known as accelerated aging syndrome, which you see listed here. Hutchinson-Gilford is the one at the top. That's the one I studied, and that's the most well-known. It's the most severe form of progeria, and it basically dramatically accelerates aging. And the idea was, like, by studying these diseases, can we learn something about aging that we would never have thought of before? Like, is there something really unique there that would really just take us into a new dimension of understanding aging? That was the hope. And some people believe that. Some people believed, oh, it doesn't really have much to do with aging. There was a lot of different opinions. I believe now, I think it doesn't actually say, it doesn't tell us anything hugely unique. Like, there's nothing like truly that we would never have thought of. No, that's not the case. But on the other hand, I believe these diseases in Hutchinson-Gilford have taught us something very important as well. And that is sort of how I view science now, that you know, we all make hypotheses, we test them, and our hypothesis may not be confirmed. Like, we may not get the answer, but we still can gain a huge amount of knowledge doing those experiments, new knowledge. That's basically the basis of empirical science. So I believe that we did learn a lot from progeria. What did we learn? I'll answer that as we go forward. So this is a mother and child, and you can see that her son kind of looks in many ways older than she does. So this is a very typical presentation of progeria, dramatic aging, like profoundly accelerated aging. And it's important to realize that this is not just something that looks like aging. So we're seeing heart disease, arthritis, joint dislocation, muscle loss, aged skin, hair loss. I mean, basically everything that we associate with aging, but at a dramatically accelerated rate. So children with progeria look like this at younger than 10 years old. I mean, it starts in infancy, basically. There's also some other things that don't appear to be related to aging, such as growth retardation. So they don't really grow. They don't really grow above several feet in height. And you also see strange things like recessed jaw. They can even reabsorb their tips of their fingers. They can lose their clavicles. You can see here, there's a resorption of the clavicle bones, and so on. And that was a real mystery as well, in addition to the aging, like what is actually going on with the tissue. I believe they're absolutely part of the same phenomenon. So they're caused by the same thing, the same reason. And that I believe is cellular senescence. So if your cells cannot divide, you will not grow. If your cells cannot divide, you will start to lose tissue from your fingers, from your clavicle. If your cells cannot divide, you will have delayed tooth formation, and so on and so forth. So these sort of features, these pathological findings that were thought to be not connected to aging, are actually part of the same phenomenon, which is cellular senescence. So as we go through, I'll explain why I believe what we learned about aging from progeria was not something that we would never have thought of, but rather it confirms that cellular senescence is hugely important for understanding aging. So I was involved in the identification of the gene, again in the early 2000s for progeria. And it was a long project. Francis Collins was the director of this project at the NIH. And I won't go into all of the details, but you can see at the top there a normal sequence of the gene that's mutated, Lamin A, And excuse me, in progeria, there's a single base change, a C to T, you can see on the second line. And it's like that's one nucleotide out of the 3 billion in the human genome that was changed. So it was a C to T mutation. You can see that on panel B, that the top of the larger box, you see the normal sequence of Lamin A, which is the gene that was mutated. And in progeria, the line underneath, you see that C is turned to a T. And what that does is it doesn't actually, oddly enough, it doesn't change the protein sequence, but it changes the splicing of the gene. So on the lower panel where it says exon 11, that is exon 11 of the Lamin A gene. And that nucleotide change causes the gene to splice in the middle of an exon 11, that it should not be doing. So it basically splices out 150 nucleotides from that exon. And that leads to 50 amino acids being deleted from the protein. So the net result is you have a protein that is being produced in progeria that is missing 50 amino acids. And that has consequences for the cell. So the first thing we saw right away was that in cells from patients with progeria, that you get this distortion in the nucleus. So this down here is like a normal human cell nucleus. This is stained for Lamin A. So this on the bottom panel is the normal cell, the very bottom one is the normal cell. You can see it has like a nice round oval nucleus. The green is staining for Lamin A, which is the protein that's mutated in progeria. And the red is staining for DNA. And on the right, you see them merge together. So what we saw right away was that like this Lamin A mutation, and the upper three rows are progeria cell lines, that it causes this profound distortion in the nucleus. So you see this irregular shape and irregular nuclear membrane, which is you don't really see that in any other disease. Like it's a unique finding. So that was like, let me put this in context. This was very soon after identifying what the mutation was in the disease. So we wanted to test out how that might lead to aging, testing different things. So in the next few slides, I'll show you other types of damage that we detected in the cells. Understand, like, why, if we mutate this gene, this protein, do we get progeria, accelerated aging? And various types of damage were found. So this is like a distortion in the nucleus. We also saw impaired DNA double-strand break. So the two columns on the left are normal cell lines. We irradiated them. And you see over a time course, so the upper panel, the upper row is unirradiated. The second row is at 30 minutes. The third row is at 12 hours, and the fourth row is at 24 hours. And you see that in the two normal cell lines, which are the two on the left, the DNA double-strand breaks, which are indicated by the purple speckling, are basically almost disappeared at 24 hours. So the bottom two lower left normal cell lines. Whereas in progeria, you have this persistence of the DNA double-strand break, and that's represented also on the graph on the right. So the progeria cells are basically not repairing their DNA double-strand breaks efficiently at all. And there's even a kind of a basis DNA damage going on even before irradiation, as you can see in the upper right. So even prior to irradiation, there seemed to be some like low-level continuous DNA breaks being generated. If you compare the two on the upper right to the two on the upper left, which are the normal cells, you can see this accumulation of DNA break. So again, more damage. We also found that if we put progerin, which is the mutated form of Lamin A, into normal cells, that we could accelerate telomere loss. So this is staining for telomeres, DNA specific to telomeres. The right is a control cell, the left is a progeria cell. We stain them with the telomere marker, put them through what's known as a FACS sorter, and it turns out that if you put the mutated Lamin A into normal cells, you can actually accelerate telomere loss. So again, another form of damage, another form of DNA damage. This is staining for epigenetic changes. We see on the left a normal cell line. The upper left, is a normal control cell line, stained for Lamin A in red. The green is a marker for what's known as heterochromatin. This means genes that are DNA that is compacted down and is not expressing genes. And you need a certain amount of heterochromatin in normal cells. Like, you don't want all the genes being expressed. You don't want everything being activated. You need a certain amount of heterochromatin in normal cells. So you see that in the upper middle panel. There's a green staining there. And then the merging of the two is on the right. On the lower row, you see progeria. Again, you see the irregular nucleus that's always seen. But you also see a loss of heterochromatin, which what that means is genes are being expressed that should not be expressed. If you lose heterochromatin, you get something called euchromatin, which means the genes are being activated that should not normally be activated. So the message, what I'm getting at here, I'm not going into great detail with all of these, is that we just found various types of damage, telomere, DNA double strand break, epigenetic changes. Also, another thing we found, gene pathway activation. So this was with Alex Zhavaronkov in silico. If you look at progeria cells, you look at the activation gene expression pathways, they resemble more old and middle-aged cells in terms of their gene activation pathways than they do resemble younger cells. Even the pathways are changed to an older pattern. So what does it all mean? What is it telling us? There's various types of accumulations of damage in these progeria cells. So we have, this is a normal cell here. Lamin A is usually lining the outer edge of the nucleus. So it laminates the cell. That's the origin of the term. And basically, it's causing all kinds of different damage inside the nucleus. It's changing gene expression and epigenetics, causing DNA repair defects. It's causing apoptosis, damaging telomeres. So at this point, it doesn't really tell us anything that we would never have thought of before. There's nothing like that jumps out, oh, we would never have imagined that. But what it does show is that, or I'll get to in a moment, is that the cells in progeria are becoming senescent very early. And you find that with all of the accelerated aging diseases. So in the earlier slide, I showed a list of different diseases, so-called accelerated aging diseases. And those are not caused by Lamin A mutation. They can be caused by mutations in different genes, RECQ, DNA repair enzymes, and so on. So they have a completely different cause, a completely different etiology, but you get a similar outcome, like a similar phenotype at the end, the similar result, despite different mutation. What they all have in common is that in these diseases, you get dramatically accelerated cellular senescence. So you don't necessarily get exactly the same type of damage in each disease. But in all the cases, that damage leads to cellular senescence. And you're probably familiar with this idea of the Hayflick limit, that cells, human cells or any mammalian cell will eventually senesce. So This is on the x-axis, we have the number of cell divisions. Y is proliferative capacity. Over time, the cells will lose their ability to divide. They will literally stop dividing. The only cases where that can be bypassed is in cancer. So some cancer cells can reactivate cell division. And that's what gives cancer cells their immortality, and that's what makes them so difficult to deal with. And the other case where you see this infinite replicative lifespan is in germ cells and embryonic cells. So they do have the ability to bypass this Hayflick limit. But the point here is that in the accelerated aging diseases, you get this dramatic decline in cell division, way more profound than you would see in a normal human being, greatly accelerated. And this is another experiment we did to prove that the progeria cells have increased levels of early senescence. This is staining for a marker. It's called senescence-associated beta-galactosidase. And you can see on the two cells on the left, the two cell lines on the left, staining for this marker of senescence, that you see it very early in the progeria cells. Whereas in the normal cells on the right, the two panels on the right, you do not see this marker. And this has been replicated many times. We know this is a fact. I've grown progeria cells in culture, and they literally stop growing very quickly. Like they're almost impossible to grow. You can grow them a few population doublings, and then they cease. And it's also been shown for other premature aging diseases. So the causes are, I want to emphasize this point. The causes are slightly different for each of these diseases, but the outcome is the same: senescence and dramatically accelerated aging. So this led to the conclusion for me that Lamin A, the gene that is mutated in progeria, is regulating senescence. So you're basically starting out at the top there. You have this nuclear lamina disorganization, which is what the protein is doing. And then that causes all these other consequences that I've been talking about, some of which I've mentioned through those different experiments. But they all converge, they all lead to the same endpoint, which is senescence. And I was looking at this picture sometime later, after all of these experiments, with the knowledge of what we saw. And what struck me is, when I look at this picture, what I see in the child with progeria are visible signs of cellular senescence, like macroscopic representation of cellular senescence. So you can see a massive depletion of fat cells, adipocytes, loss of hair follicle stem cells. You see loss of muscle. You see loss of other tissues. You see loss of bone. Basically, all the tissues are being depleted. They're being destroyed because the cells are not replicating. Compare him to his mother. She has subcutaneous fat, subcutaneous adipocytes. She has hair follicle stem cells. Even things like hair graying are really caused by senescence, like you lose proliferation of the melanocytes in the hair follicle. So basically, this to me is like a visible representation of cellular senescence macroscopically. And it's it was remarkable for me to see that after doing those experiments and taking in that knowledge. So that's what I believe is happening with progeria. That was the lesson for me. So there wasn't something, as I say, incredibly unique that we would never have thought of, but everything pointed to cellular senescence, which again wasn't exactly the answer we wanted, perhaps, but it's still like a profound insight. But what if we compare progeria to normal aging? In progeria, on the right there, it's caused by a mutation in a gene, Lamin A mutation. in a gene called Lamin A. That's the main risk factor, and that leads to all the things I was talking about: telomere loss, DNA double-strand breaks, epigenetic changes, stem cell depletion, cellular senescence, which also manifests as a lack of growth, lack of height, lack of tissues being maintained, resorption of bone, etc. In normal aging, we also see that, actually. So you do actually see loss of tissue, but it may be harder to see in some cases, like, so there could be, for example, like increased storage of lipids in adipocytes or something that could mask that effect, but it's still nevertheless there. That you see the telomere loss also in the cells, you see the DNA double-strand breaks, epigenetic changes, and so on. So the outcome is still converging on cellular senescence. Like, it's just that the cause in progeria is this accelerated damage coming from the mutation, whereas in normal aging, there's damage coming from a variety of different points. So it's this Lamin A mutation that is accelerating all of the damage. So what it told me is that it led me to this conclusion that cellular senescence is the causal nexus of aging, is the term that I use. So what does that actually mean? A causal nexus means a bridge between cause and effect. So you can have multiple causes for something and one outcome, only one result, which is aging. But they need to go through a bridge, which in this case is senescence. So you can have telomere shortening, you can have mitochondrial dysfunction, aneuploidy, so all these kinds of different damage. But what they all do is cause cellular senescence, shown there. And that leads to a loss of proliferation in the dividing cells, a loss of maintenance of tissue. If you can't maintain the tissues in your body, you're aging. So they're basically synonymous with each other. Okay, you may say, well, there's some cells that don't divide, neurons, skeletal muscle cells, they don't divide. Well, they can also undergo senescence. They acquire something called the secretory phenotype, the senescence-associated secretory phenotype, also known as SASP. So they're not necessarily they're not losing proliferation because they weren't proliferating, but they still undergo changes. They still become senescent. So this is the term I came up with. The causal nexus is synonymous with senescence. Senescence is synonymous with the causal nexus. And basically, it's the bridge between all of this damage that's occurring, which is dramatically accelerated in progeria, but leads to the same outcome. So where do we put the mutation in this sort of causal chain? So if we think of all of these factors here, like mitochondrial damage, telomere erosion, cytoplasm damage, epigenetic changes, that central column there, all that is damage. That leads to the causal nexus, the intermediate step, which is senescence, loss of proliferation. And then that leads to aging, as we see on the right there. So where does the mutation fit in? It fits in at the beginning of the causal chain. So it's basically accelerating all of those types of damage, mitochondrial damage, telomere erosion, cytoplasmic, etc. So you could again, I coined this term supracausative. It's basically initiating the damage that is then leading to cellular senescence and then aging. So that was what I learned from progeria. I'm not saying that is the end of the story. There's still a lot to do there, but that's where, again, this is science. This is where my current understanding is of it. This is how I sort of hold that knowledge in my mind. I want to go now into like the broader support for that that cellular senescence is the causal nexus of aging. Some theoretical support, and it basically goes all the way back to one of the pioneers of gerontology and evolutionary biology, August Weismann. And he was remarkably prescient. He came up with this idea, well over 100 years ago, that death takes place because a worn-out tissue these are his words, because a worn-out tissue cannot forever renew itself, and because a capacity for increase by means of cell division is not everlasting, but finite. And he did this he came to this conclusion by studying single-celled organisms and comparing them to multicellular organisms and looking at how they divided resources between what are known as germ cells and somatic cells. So he was basically studying early life and looking at how those animals regulated cell division. And he reached this remarkable conclusion from that. He was also an evolutionary biologist. So he basically put this in the context of evolution. And Michael West has also sort of further developed this idea as well over the years, that essentially life on Earth has existed for billions of years. Like we all go back, we're all descendants of the first organisms on Earth. And the way that is maintained is through cell division. So this upper line, the green, is what's known as the germ line. So there's a certain type of cell that never loses the capacity to divide. I mentioned they will just keep going. And in human beings, those will be the spermatogonia and the ovarian ova, the ovarian stem cell. And they maintain life, not just from one human generation to the next, but basically over the entire evolutionary history of the Earth. Like those cells have maintained life. They are immortal, but our somatic cells are mortal. So it's almost like you can sort of think of a branch of a river coming off from the germline, which creates an individual. But those cells are destined, or used to be destined, to die. And it's sort of like you can imagine a tributary coming off and freezing. It doesn't have the properties to keep going. So you can see this in more detail on this figure. It's basically representing the embryonic cells at the top. So if you consider each column there one individual, so imagine this is one person. They started out as embryonic stem cells. And then early during development, some of those cells became germ cells. So this happens quite early in development. Germ cells, spermatogonia or ovarian stem cells will be produced early, and then they stay through the entire life of that individual. And then the majority of the cells, all the other cells, if you follow that column down, become somatic cells, somatic stem cells, and then just basically somatic cells. So those orange cells at the bottom are the majority of our cells. They are somatic. They have a limited lifespan. They will senesce. On that second column, you can see that red cell is senescent. And they're basically destined to senesce unless we change that. And but the point is also here that those germ cells on the second row, the lighter green, can produce another generation, produce a new individual, which we see in the second column. So a whole new generation is produced from those germ cells at fertilization. And they will be embryonic cells. And then that individual will then make their own germ cells again, early in development. Their cells will become somatic and eventually senesce again. But then the cycle continues. They can at fertilization create a new individual, and so the life cycle continues. So there's no reason why cells can't be immortal, just that there are certain genes switched off in our somatic cells that render them mortal. And as I mentioned earlier, there is a way around that, which we see on the third column there, the cancer cell, and that has reactivated some of the embryonic genes. So they will reactivate telomerase, for example, reactivate other things, but it's not in a good way. So it's a kind of a corrupted form of immortality because you also have other mutations in the cells. So they can't be controlled, they can't be regulated. It is a form of immortality of the cell, but it's bad. It's not a good form of immortality. Basically the foundations of aging research were actually based on the idea of cell proliferation and cellular senescence. They may have called them different things. You know, Weissman may not have used the term senescence per se, but he was basically there already. And then Leonard Hayflick, you know, proved that that was a real phenomenon. And then I think we have further proof through the accelerated aging disease. Switching over a little bit into like how we understand or how I view aging currently. So this is not directly related to Weissman, but if we are considering an individual, you can kind of stratify aging into different layers, different levels. So at the deepest level down here, we have molecular damage, damage to the DNA, damage to mitochondria, epigenetic changes, and so on. This is what you could call molecular damage. And this is really the cause of the higher levels. So you have all this damage occurring deep down, and then that's causing these other things. Obviously, that a big one is cellular senescence, that I consider the causal nexus. Then that leads to things that we normally associate with aging: chronic inflammation, nutrient sensing, deregulation, endocrine dysfunction. And then that leads to, in turn, to seemingly independent age-related diseases. So we see heart disease, we see cancer, we see Crohn's disease, we see all these different diseases that appear to be independent of each other, but they're really all coming from this basal level of molecular damage. So it's like the cause is occurring down here, the deep level in the DNA, in the mitochondria, in the organelles of the cells, and then it propagates upward through these apparently independent diseases. So that brings us to the question: is aging a disease? So is aging a disease? I don't think we can call it a disease exactly, because it's really the cause of the disease. So I think it's more helpful to classify it as a meta-disease, which is something transcending the individual diseases and the cause of these individual diseases. So what does meta mean? You know, you probably heard that term before. Meta means like more comprehensive, transcending, or foundational, causal. So metaphysics is thought to be beyond physics, foundational to physics. It can be used to designate a newer related discipline, like metaphysics, as I mentioned. And I thought of this term meta-disease. It came to me one day, and I looked it up, and apparently it has been used before by Abraham Maslow. He used the term meta-disease to depict how the origins of physical disease are based on unresolved emotional issues. So it's not the same, it wasn't the same thing that I was thinking of, but in some ways it's similar in that he was looking for something basal disease, like beyond disease, that was causing disease. I thought of it in terms of aging. He was thinking of it in terms of emotional issues. But some of the principles are the same. So really, aging is the cause of age-related disease. it's not exactly a disease itself. Diseases, as we normally think of them, are various types of specific phenomena. Cancer, heart disease, arteriosclerosis, etc. So they're very specific. Aging is the cause of these things. And these causes, again, are occurring at the microscopic level. If we take cancer, for example, a p53 mutation is like very commonly found in different types of cancer. But it's not itself cancer. Like a p53 mutation is not cancer. But a p53 mutation can cause cancer. So it's like one is a cause, the other is an effect. Like aging is a cause, disease is the effect. So the mutation is the damage is the cause, the disease is the effect. So it doesn't quite make sense to call aging a disease, but it does kind of make sense to call it a meta disease. And you can sort of draw that out as a set in principle. Like this is a very simplified idea of this concept. You have this large set A, which is the meta disease, aging, which is caused by damage, and that is the cause of these different diseases. And then within that set, you have, say, set B, which would be cancer, and then within that set, different types of cancer. And then set C, you have, which is also a disease contained within the set of meta disease. You have heart disease. And you could even, if you wanted to, like include cosmetic changes like graying and skin changes and so on. So even those you could, in theory, contain within the meta disease set. It's actually Mikhail Blagosklonia, another aging researcher, said something similar along these lines. He said, a zoo contains many different types of animals, but it is not itself an animal. And I think we have to be careful, like how we define things. But I think it's a useful model, this set theory with meta disease as aging and then causing all of the other things. And it relates to something called linguistic relativity, also known as the Sapir-Whorf hypothesis. If we create new terms, it actually helps our thinking. It can sort of change if we create new words to define things, it can aid the way that we think of them. It can actually facilitate new ways of thinking about them. And this is an old idea known as linguistic relativity or Sapir-Whorf hypothesis, that the more words we have for something, the greater our perception of it. And there's like various examples. The Himba tribe have many different words for green, and it's been found that they have a remarkable perception of green color. Eskimos, the well-known example of the different types of words they have for snow, and this is a fact. Like they can perceive different types of snow. So it's I think as we go forward, not necessarily just in aging itself or even in biology, but it's always useful to try to make new words that help us think. And they're kind of sort of like putting a piton or like a wedge into a cliff face. Like, boom, this is a new word. We're going to define it. And, it's sort of like knowledge is sort of like climbing this cliff. Like we need new words to help us think. And it probably operates through synaptic plasticity. Like you create a new word, it probably causes some change in the. So what can we do about it? If it's up to me, I think it's wise to focus on cellular senescence. I think this is a smart thing to do. There's also, of course, epigenetic changes, which is a big thing now. I tend to think that cellular senescence is more important than epigenetic changes. And things like reprogramming are probably reversing cellular senescence. It's more important than reversing the disdifferentiated state of the cell. But I won't go into that deeply at this point, but I think I lean more towards cellular senescence as being primary rather than epigenetic changes. And in any case, like when we are thinking about defeating aging, I think if we can focus on something like cellular senescence, maybe epigenetic changes too, like but one or two, three possibly like major mechanisms, then we can sort of fly over the walls of the maze. Like, you know, each of those twists and turns goes to a different disease. You know, you could spend years, decades trying to understand an individual disease, if ever, whereas you could just jump over the walls and get out of the maze simply by refusing to cooperate with the maze. You make your own rules. You define how you're going to get out. So I think reprogramming is a good way to go about this. As I said, I see it more in terms of reversing senescence than epigenetic disdifferentiation. And we've done some experiments ourselves at Howard, like basically reversing, reprogramming progeria cells. So the upper panel there is staining for embryonic genes. So these cells started off as fibroblasts, you know, just as totally somatic cells. And we're staining them for nanog and OCT4, which are embryonic. So those cells have been reprogrammed. And you can do that not just with normal cells, but with progeria, like even progeria cells can be reprogrammed. So I think like reprogramming is a potentially very powerful technology. And again, I see it more as reversing senescence than epigenetic disdifferentiation, but obviously, I mean, epigenetics is important. I just haven't personally quite decided on it yet. However, we still we can reprogram. We can reprogram cells. That's becoming like a well-developed technology, but that's not enough. Like, because we need to go further than that. And Bill is going to talk about this more, I believe. Basically, you know, it needs to be applied in more powerful ways to regenerate organs. So we can reprogram, but we need to go up the scale. We can repair the damage. We can repair the molecular damage. We can lengthen telomeres. We can even eliminate cells with senolytics, which I won't go into. But basically, we can do all this, but we need to regenerate organs. It's not just enough to reprogram the cells. Like, we need to go up to higher scales on this stratified system. So that's about it for the progeria and aging itself. In this last third, I want to go into the philosophical implications of what this means to me, like what I think it means for humanity. I want to start with the simulation hypothesis. So you probably all heard of this now. You know, Elon Musk has been talking about it, various philosophers, Nick Bostrom and others have been talking about this for some time. And it's basically the idea that all reality is including the Earth and the universe, it's basically a simulation of some kind. So a technology that seems realistic to convince its inhabitants that it's real, used in movies like The Matrix and so on. I don't necessarily believe that we're in a computer simulation exactly. You know, I don't quite see it that way. But I think there may well be deeper aspects of reality beyond what we perceive with our five senses. So there could be like other aspects of reality that were imperceptible to us that are generating this material world. And if we consider it over time, you know, if we consider the universe over a very large time scale, so this time axis at the bottom there is going all the way back to the Big Bang, and potentially even before that, like, there must have been something metaphysical before the Big Bang. The ancient Greeks called it the arche, and there's like a lot of interesting philosophy there. But basically, what it shows us is that over time, the potential, the metaphysical potential at the beginning of the universe was essentially infinite. So anything could happen, but nothing was yet actualized. Nothing had actually become reality. But over time, there's been a greater and greater conversion of that potential into actuality, into greater and greater complexity. And we are now at this point, as human beings, perhaps somewhere in the middle of this whole journey, where some of the potential has been converted into actuality. And according to some religious thinkers, Teilhard de Chardin and others, like you extrapolate this point way into the future, you arrive at the omega point of God. And so you could look at this and say, well, as human beings, maybe we have like a huge responsibility now to continue this, this journey of conversion of potential into actuality, which is also known as entelechy. Like, can we contribute entelechy to the universe? And basically, each individual can, in theory, contribute their own development to the universe. So this is like, on the left here, we see Maslow's hierarchy. We all have needs, survival needs at the bottom, safety needs. We need to belong. We have self-esteem needs. We have self-actualization needs. And everyone, probably a lot of people have heard of this, Maslow's hierarchy. But he did, recently there's been the realization that he actually had a sixth level, which he called self-transcendence. And he didn't really talk about it much, like it was more in his private writings. But it's really, you can think of it as, if we can self-transcend, we can actually contribute more to the development of the universe, which is shown on the right. So those same things I showed on the previous diagram are now shown as the universe's own kind of Maslow's hierarchy. And we can kind of like join ourselves to this self-actualization of the cosmos. But it takes kind of getting up to these higher levels, self-actualization and possibly self-transcendence, before we can do that. If we're stuck here, like in the lower levels, in survival needs, in safety need, we're never going to be able to really contribute to realization of the omega point. So, humanity is kind of holding itself back in that way. Things like wars and conflicts and, all kinds of disagreements and injustices, etc., are really causing individuals to be stuck, and that also leads to a potential sort of freezing of the development of life itself. So I think when we do go about solving aging, we need to consider it in the context of other issues that humanity is facing. We can't just solve aging and just say, well, forget about everything else. Like, that could be potentially disastrous, I think. So, we're also at this nexus point of a lot of other things occurring at the same time. Search for extraterrestrial intelligence. There's more and more data, information coming out about UAPs, and who knows where that's going to go. Artificial general intelligence, that's coming very soon. This is coming. How is that going to affect humanity? Exploration of the solar system. Elon Musk wants to go to Mars. I think that's a good thing. Want to go back to the moon. We need these things, but economic systems, maybe there can be improvements there. So it's like we need to, I think we can't solve these things in isolation. Like we need to consider them collectively and work on them together holistically. And in terms of the simulation itself, why would there be, you can ask the question, the rhetorical question, like what would be the purpose of the simulation? What would it be designed for? One potential answer is it's a test. It's a means to elevate consciousness. So within that diagram that I showed earlier of the projection of the life of the universe, if we are in a simulation, there must be a reason for it. And one potential explanation is that it's a way to make life more complex, more conscious, to evolve life, to evolve consciousness over time. And it could be, this is getting quite speculative now, obviously. This is kind of very deep. But it could be, if the simulation wanted to design a problem that would require humanity to evolve, solving aging could be a way to do that as a means to elevate consciousness within the simulation. It would be a great challenge within the simulation, like the hero's journey collectively for humanity. You probably heard of Joseph Campbell's hero's journey, which is usually applied to individuals, but it could also be applied to humanity itself. Like this is our hero's journey. We have a call to adventure. We could refuse the call. I mean, certainly none of us have, which is great. We may meet mentors, but then we cross the threshold. We go into an unknown world, which is the lower part of that figure, the unknown. There's tests, there's allies, there's enemies. We approach a challenge, an ordeal, and then we may receive a reward of some kind. Maybe it's understanding aging. Then we have to go back. There's like a final test, resurrection, and then returning with the elixir. And this is like humanity change. So it could be applied to not just the individual, but humanity itself. And we're getting towards the end of this talk now, but this brings us to Nikolai Fyodorov, who is in your creed that we said at the beginning. He basically realized this. I think, like he basically realized this a long time ago. He was a founder of the Russian cosmism movement, which was really a precursor to transhumanism. Yep, and what he believed in was radical life extension, physical immortality, resurrection of the dead, using scientific means. And he coined this term, the common task. That's what he called it. It's a creation of a universal brotherhood, and something that would unite humanity and to make us worthy to go forward into the universe, to govern the universe. And he saw like mortality, death, as the most obvious indicator that we were still not ready. We're imperfect. And he also saw it as the underlying reason for most evil and nihilism in the world. And he saw this as like a profound challenge that we had to address. But he also saw it as the way that it could unite all people of Earth, regardless of race, nationality, sex, gender, citizenship, wealth. Like it's the uniting principle of overcoming death, the common task. This is our common task. And I realized also that his ideas recapitulate alchemy. So alchemy was an older tradition that came before Fyodorov, but there were some similar goals. They were trying to transmute base metals into gold, but that's really an allegory for transmutation of consciousness, from lower to higher level of consciousness. But they were also very much dedicated to creation of an elixir of immortality, creation of a universal panacea to cure all disease, purification of the human body and soul from the alchemical magnum opus. So it was really a very deep philosophical tradition. And it actually has some parallels with the common task. And the Philosopher's Stone, of course, was also connected with alchemy. But it really represents enlightenment, the philosopher's stone, it's not like a stone, it's not a physical object. It's kind of an allegory for enlightened mind or higher intelligence, which may also be now, we may have beginnings of contributions from artificial intelligence to that as well, in terms of the philosopher's stone. So in practical terms, what does this mean? What can we actually do? What does it mean for us here? One thing is sure, like only 1 or 2 generations will ever have the choice to fight for immortality. Because in the past, it was simply impossible. In the past, the alchemists were born at the wrong time. Fyodorov was born at they saw it in principle. They saw what was coming, maybe. You know, they knew that our time would come, but they were born at the wrong time. So no matter how smart they were, no matter what their ideas were, etc., it was beyond them. You know, alchemists, you know, all the other greats. And in the future, it will be solved. You know, in a couple of generations from now, there won't be any fight. You know, there won't be any challenge. So it's a very unique challenge that will only ever come, even whether it's a simulation or not, it doesn't really matter. It will, you know, this challenge will only be now. And we can expand this figure a little bit. There may be like a supercritical window of time in this, even within this narrow window, where the people that are born at the early stage of that time, of this window, have to do more. Like if they want to achieve physical immortality themselves, the individual, you know, and this time scale is just illustrative. I put 50s, 60s on the left there. It could be different. I was actually discussing this with ChatGPT, and it came up with different. So, yeah. But, you know, what I'm getting at is if those individuals here, for them to reach physical immortality, they have to do more than those individuals on the right. And the differences would be, for example, creating institutional changes, sociological changes, changing the world in different ways. Some of you here are doing that. But even you know, people born later, they still have to make the choices they make will also determine whether they achieve physical immortality, lifestyle choices, development of technology, and so on. So there is some difference, but what is striking is success or failure could come down to a matter of months. You know, so this was another thing I worked with ChatGPT on. Like you have individual A, born in 1970, they're healthy, avoiding risky behaviors, they survived to 2050. And everything is fine. You have the same individual or similar individual born in 1970 and make similar choices, but they don't avoid a preventable health, like say they have some habit or something that causes something, some pathology to occur. They will not make it, and they, excuse me, these slides are out of sync. They will not. You know, even though they're born at the same time and, you know, many aspects of their lives are similar, some failure of individual B to prevent a health issue could cause them to lose that grasping of physical immortality by a matter of months. So in any case, what we need to realize is that no single individual can solve this problem. Like, we have to work together. It's something that can bring humanity together. It's the common task. You know, this is something that you can unite us all. You know, it is the great change, if you want to think of it that way. Again, whether it's a simulation or not, it can be the great change. And then the last slide I want to, it could also be, you know, and this is speculative, this is, you know, even more speculative than the previous slide. Say we don't do this now, like we don't find a way to do this, to erase our differences, to work together, to create harmony, using aging, defeating aging as the great cause, of the common task. Say we don't do it, and it could cause like a disconnection between the acceleration of technology and human consciousness. It could cause them to separate too much. And we're kind of at this bifurcation point where we could literally destroy civilization if we don't elevate our minds. And we could go either way. And maybe the common task is the way to do that.
We've gone over the Q&A time, but can you do questions in the hall?
Yeah.
All right, ladies and gentlemen, Dr. Csoka, thank you. He flew all the way in from Washington, D.C. quite late last night, and we're so glad that you're here. We have compliments of Hoffman Cryonics Financial Planning, the flowers of the day, the flowers of the month. We want to thank Rudy Online, who, by the way, is our volunteer of the month online, Rudy Hoffman. And come on, Rudy Hoffman! And oh, by the way, ladies and gentlemen, he's giving these flowers to you as you leave. Please take a flower with you. Rudy said, take them away and have a flower, and happy Thanksgiving to you. Let's bring up the founder of the Church of Perpetual Life and my good friend, Mr. Bill Faloon. Bill.
Fantastic. Now, a lot of what you saw there, I'm going to present in a little bit of a different way, but this is going to also involve rejuvenation scientific updates, some of which I think you'll find very compelling. Let's go back to 1955. The most powerful man in the world suffers a massive heart attack. Dwight D. Eisenhower, president, World War II hero. This guy accomplished a lot. He was well respected, but his coronary arteries occluded through a massive heart attack. He was in bed for months. There's nothing they could do to unocclude his arteries, by the way. Back then, there was no stenting, no bypass surgery. Had a heart attack, lay in bed. Some people got out of bed. Some people died in bed. That was it. 1957, throws a stroke. And then he suffered for 14 miserable years with these occluded coronary arteries. They couldn't do a thing about either reopening the arteries or putting him on any kind of program to prevent him from continuing to occur. So his suffering was well known for people who knew him. No one wanted to die the way Dwight D. Eisenhower did over a 14-year miserable period. 1955, 1 year after I was born. And he was unfortunately born too late to benefit from all the technologies that have evolved in reversing coronary atherosclerosis. The very same year, Lyndon Johnson, he was the Senate Majority Leader, the second most powerful man in the world in many respects. He also suffered a massive heart attack, suffered chronic angina pain. They couldn't reopen his blocked arteries back in those days. And he resigned from the re-election at the young age of 59. And I'm thinking, I'm 70 years old right now. I'm probably working harder than ever. But it's not because of any genetic advantage over Lyndon Johnson. He had family history of heart disease. So do I. But I've had access to all kinds of technologies to at least delay the onset of coronary atherosclerosis. He didn't. And at age 64, he died. And he knew that was going to happen. One of the reasons he quit at age 59 is he knew the Johnson men didn't live past age 60 for the most part. They pretty much all had heart attacks. Of course, they smoked cigarettes. They ate the worst kind of foods. They had nothing to really prevent the occlusion of their coronary arteries, and they suffered quite a bit. And what has happened over the decades is improvements. Nowadays, they use stents. But just identifying the best ways of doing coronary bypass surgery, well, it took a lot of time. It took time, but the longer you lived, the better your odds were of preventing a heart attack and stroke and other problems, and also treating it. You could be rushed to a hospital, and they would reopen blocked coronary arteries. Lyndon Johnson, well, he missed it by just about a decade, a little bit over a decade. Had he just been born a little sooner, he would have then benefited from all this and not been in a position that so many others have. But you look at other former presidents, obviously it's a high pressure jobs because they all had massive coronary artery occlusions. All of these individuals would likely be deceased now. Definitely Dick Cheney. He wrote a book on it about the marvels of modern medicine that were able to, every single time his heart was failing, figure out a way around it. Bypass surgery, stenting, and then finally a heart transplant to keep him alive. And he's still alive at advanced ages compared to Lyndon Johnson. Not that long ago, Lyndon Johnson dies at age 64 in 1973. These former presidents are still alive. And again, coronary atherosclerosis. No matter how much you're working to keep your arteries clean, hate to say it, it's a natural phenomenon. It has nothing to do with modern day practices, been around forever, including the ancient Egyptian mummies. They've all suffered atherosclerosis. It's just one of those problems that we have to work with technology to overcome. Now, the good news is, since 1980, the rate of heart attack deaths went down, huge 56% decline, and it's now going back up because of, well, obesity and type 2 diabetes, metabolic syndrome. We're now eating ourselves into early types of coronary artery disease and neuropathies, dementias, all kinds of problems are occurring. And what we're able to do nowadays, if we want to, by attending a church like this or paying attention to alternative health publications or just going to your cardiologist, you have all kinds of ways to reduce your risk of having a sudden death heart attack or a heart attack that cripples you so you suffer chronic heart failure until you die. You can reduce your risk of stroke. But none of this was available for Lyndon Johnson. They didn't know how to prevent it. They didn't know how to reverse it. They didn't know how to treat it. That was his dilemma. He simply was born too soon. And this is what happened in 1968. I watched this when I was a kid watching this on TV.
I shall not seek, and I will not accept the nomination of my party for another term as your president.
When you think about how hard these individuals work to achieve this status, and we all work hard to achieve whatever status we are, but to be taken out at that young age. This individual, a little bit unique, 100 years old, Jimmy Carter, and he is only alive today because of technology. Yeah, he had some good longevity genes in him. None of his other siblings did, by the way, but he managed to work into his 80s and 90s. But you look at 2015, terminal cancer. He had a melanoma metastasized to his brain. And he made an announcement, I'm terminally ill, I'm going to die just the way it is. And the doctor said, let's try an experimental immune therapy. It doesn't work on everybody. Let's see if it works on you. Keytruda was the drug I believe they used. It's one of those checkpoint inhibitors. And it cured him of the cancer. He was shocked. So he continued living. And, well, what happens with older people is falls, fractures, usually death. He fell, had a fracture, brain bleed, still survived it. And he entered hospice back in 2022, saying, I don't have much longer to live. He's still alive. He's still alive. He's not in good shape. But hey, he made it to age 100. Think about Lyndon Johnson, age 64. But he would not have made it to age 100 without the advance of medical technology, something that a lot of people just don't appreciate. Let's look at where we are right now. We can deal with heart disease and certain malignancies. Well, we're also aging to death. Good news is in early 2024, young plasma enriched with specific exosomes that we think may have contained certain Yamanaka transcription factors. So they get the benefit of both transcription factors and young plasma. They reversed aging in the animal model, and that they were advancing that to dogs. Young plasma reversed epigenetic aging in old rats, increased their median lifespan about 7 years. This is a study we help fund through the various charitable work that we do. We have no commercial interest in this. And then another group, number 3, they used the OSK transcription factors to reverse epigenetic age in older animals. In doing so, they extended remaining lifespan, and they're now advancing that into beagles in a way that they're seeing it. This is what they're telling us. They're seeing age reversal occur in beagles. Good news about that is when they usually see a benefit in beagles, that translates often into humans. So this is being migrated now from mirroring mice rats into the primate model, into the green African monkey, so that we can see how well that reverses aging, that being OSK transcription factors. And for those who don't know, another refresher lesson, OSKM, these are the 4 transcription factors that have cell reprogramming benefits, meaning they can take an old cell and reprogram it back down into a younger cell from a functional standpoint, a structural standpoint, so these older cells will function in a way to, well, make us younger like it did the animals. OSKM is the acronym, and the one that we're focused on right now is just OSK. It may be that the 3 out of 4 of them will work better and have less of a potential side effect risk. That's CMYC. That is something that stimulates cellular propagation. Some people are afraid of that causing cancer. Hasn't been doing it, by the way, in the studies, but nonetheless, OSK is what we are experimenting with. And the data on systemic use of Yamanaka factors, I've shown you this before, but I just want to remind people, this has been already proven to work in 2022 by the Salk Institute. They showed partial cell reprogramming in vivo in whole mice. It was used and there weren't any toxicity factors using the OSKM. They got age reversal without toxicity. This made international headline news, and what it was able to show is cellular reprogramming. You heard something about that with the previous talk, the idea of cellular senescence killing us. Well, of course it does. But if we can reprogram our older cells, our aging cells, back into younger cells, well, we get to live a lot longer. We lower inflammation. We reduce the senescent associated secretory phenotype. Those are those senescent cells spewing out protein-degrading enzymes and inflammatory factors that cause us to prematurely age and die. Move forward to 2024 and another OSK study, another Yamanaka transcription factor study. Transcription factors, by the way, are proteins that turn on and off genes. If we use the right transcription factor, we turns on the beneficial genes that confer youth and health and turn off the genes that are causing us to degenerate and age. This is what we want to see happen in old humans. And what the study showed is, well, OSK therapy, it was only partially used, by the way, partial reprogramming. It increased remaining lifespan, improved the health of compared to the control mice, and it reversed aging in the heart and the liver as measured by DNA methylation epigenetic age markers. And I think if people who are suffering from heart failure, liver failure, renal failure, dementia, and if this therapy continues to demonstrate efficacy, we're going to be able to reverse aging across the board, including in human skin cells. Well, not only reverse aging, we will look younger. And for a lot of people, it's very important for that to occur. So this remarkable study, over a 100% extension in remaining lifespan. Now, that's not total lifespan, but it's the amount of time that they were allowed to continue to remain alive. And they used a 2-part viral vector to introduce the OSK into the cells systemically. We're now looking at non-viral ways of doing that, by the way. And these mice were the equivalent of 77 years old. And they were able to partially reprogram them, and in doing so, increase their lifespan, improve their frailty scores, and, get them to live longer. If you were a control group, that's unfortunate. You died in a little bit over 8 weeks. The ones getting the OSK, they lived about 18 weeks. So you see this extension of remaining lifespan, which is really dramatic. But what I've said before, I've shown these slides before, but I want to remind people about these OSK factors. The scientists who did the work only delivered a tiny fraction of the intended OSK dose, and they still got the most remarkable results that we know of in history. And the good news is the history keeps moving forward, technology keeps moving forward. So this is a new study. We haven't talked about this church yet. This is one that we also help fund through our charitable efforts. The work I do is charitable. We're seeking to extend lifespan and excite the world in such a way that they prioritize aging research over building better weapons, over everything else that people squander money on, as opposed to saving our lives. This study was able to show an improvement. And just so you understand, what they did here is they injected with a needle right through the skull of mice the Yamanaka transcription factors, all 4 of them, OSKM. And what's important is this is the part of the brain that's important for new memories, learning, emotions. It's a small part of our brain. It's important, and it degenerates with aging. And what they did is by injecting the OSKM, Yamanaka factors, into that brain region, the hippocampal brain region, they improved learning performance. And how many of us here at our age realize we don't pick up and learn things as well as we used to when we were younger? It might be a little bit challenging to go back to college and memorize a bunch of information and pass a test the way we did in our youth. So learning performance improved in old mice injected with these Yamanaka factors directly into the brain. I'm not suggesting anyone consider that, by the way, but the fact is there wasn't any toxicity the way they did it. They improved spatial memory. They rejuvenated the hippocampal epigenome, meaning they made it younger. And, they were able to see trends towards age reversal age reversal and hippocampal region of the brain in this study published just a couple months ago. And this is something that I'm really proud of the way we're able to do this research in rather efficient ways to get rather rapid results. But what we're doing is continuing to verify the efficacy of Yamanaka transcription factors across the board. And to show you graphically how well this works, now that red line there is the control animals. And the time they take to get out of a room, let's say, that's on fire. Let's say there's a fire right over there. You want to get out of the room there. Well, young people will get out much faster than older people, just the way it is. And so the old control, it takes them longer to react to something, whereas the younger old animals treated with the OSKM, and again, this was injected directly into their brains, they were able to reduce this latency period by 36%. So it's a really nice improvement that we were able to show in an experiment that virtually no one in the world would ever fund except people like us. Again, we're seeking to advance the science, and by doing this, we stimulate others. And this is another graph of how well it worked. But I do want to put this in context here, this improvement in learning. The red dot right across the top is the old control group. That's just like most of us, frankly. We're aging. We don't want to be that way. And then that blue is the improvement in response to the OSKM, direct injection into the brain. The young group, though, they're still doing better. We still have to improve this, make it work better. We're not there yet. But this is another graph showing effect on memory. And again, the young mice in this study, and higher is not good. Well, I guess it is good in this particular one. The young ones are doing well. The old control, by this measure, they're doing rather poorly. And then the old OSKM, they're doing better. They're actually doing twice as well as the old control group, but still not as well as the young group. Our mission, we want to get that red or that green of the OSKM animals back up to that of the young ones. So I'm going to talk about another study. That was one study we helped to fund. This is another one. And I don't think anyone here would want their brain to shrink. It does shrink with aging, by the way. So we want to make sure we maintain our neocortex. It's what makes us human. It's what we want to try to make happen. And this study was fascinating what they did. This is just a graph for neocortex. We have more of it than any other species out there, which is why we're smarter. And this study used the cellular reprogramming Yamanaka transcription factors, and they were able to improve the structure, grow more neocortex. They were able to show enhanced cognitive skills, long-term intermittent reprogramming. By the way, with Yamanaka factors, it's an on-off situation. You put them you turn them on, and at some point you want to turn them off. You don't want them going full speed all the time. It could make you too young, and that may not be healthy for you. So we are experimenting with different types of therapies and scheduling. But anyway, long-term administration, but partially reprogramming it in a way improved the Alzheimer's model. So this chart is the one that I think is most impressive. This is the same study, and they use these Yamanaka factors. We've all heard of beta amyloid. It's one of those structural defects seen in Alzheimer's patients. They do have problems with the accumulation of beta amyloid plaque, and it clogs up their neurons. They just don't function very well. And the orange bars there, you see the control group on the left, and they've got a lot of beta amyloid accumulating. Their neuronal function is deteriorating, and then the beta amyloid in the treated group with the Yamanaka factors, it's a fraction. This is a meaningful graphic, which you can clearly see the benefits of Yamanaka factors. It improved cognitive performance, by the way, but they were able to show structural benefits in response to the Yamanaka factor expression induced in these older mice. Just absolutely dynamic information. And this is another part of the study. And this may shock you, but they took the, let's say, gestational mice. This is mice in the mother's belly. They injected the brains of those very small mice with Yamanaka factors to see what would happen. And guess what? Those mice injected with Yamanaka factors in their mother's belly, they were smarter, they had greater social skills, they had just better performance in many, many ways of measuring. It worked both in the early stage of human development or mouse development. It also worked in old animals to reverse all kinds of structural problems with aging. But just imagine if this translates into people. Now, women who become pregnant nowadays are given prenatal vitamins. It's just a way to make the kid healthier, avoid neural tube defects. Well, at some point, pregnant women may very well have their fetus injected with Yamanaka factors so the kid can be smarter and be socially more compatible. Wouldn't that be wonderful if we could have better kids, smarter kids, kids that don't go and do crazy things, be it the kind of crazy things you read about in the newspaper or just the ones that people do as individuals. So this was an incredible verification that we're on the right track with these Yamanaka transcription factors. I've shown this before, but before 2006, no one thought this was possible. They ridiculed the idea of reprogramming cells back into a younger state. They proved it in 2011 with centenarian human cells. 2022, they reversed aging systemically in old mice. This was Salk Institute and Harvard. They were showing age reversal to occur, and where we're going right now, monkeys and into humans as fast as we could possibly do that. But I have to remind everybody, before 2006, no one thought this was possible. And once it was demonstrated possible, it's moved, unfortunately too slow for most of us. We wanted it to happen really fast. From 2006 to 2024, we're moving it into whole animals. So to remind people of the predicament we're in right now, if we want to die sooner, all we have to do is follow just one of those stair steps there that so many people go through during life. They misbehave with their diet, with their use of alcohol, tobacco, drugs. They don't eat the right foods. They neglect preventative care. They don't get the diagnostics they should. They leave an unhealthy lifestyle, and they die sooner. An absolute fact. No one would ever refute what you see right up there. And I like to show my house of optimal health as often as I can, because there are so many people who feel there are ways to delay aging and they don't have to worry about the fundamentals. Well, you do. And I've been doing this now since 1977. I've had people tell me I don't need to follow every one of those steps on level 1 because I'm doing something else to improve my health. I can tell you this, it simply doesn't work. Everything you see there, your lipids, your blood pressure, your glucose levels, your sleep, your homocysteine, your coagulation, you can't let one of those be out of balance. All it takes is one, you throw a massive stroke or develop a malignancy, and then you die before we can reverse your aging process. And we don't want to be in this situation.
I'm talking to Tom Johnston, the press secretary for Lyndon Johnson, who has reported that the 36th President of the United States died this afternoon. He died of a heart attack. He had been suffering from heart ailments for some time. He'd had two serious previous heart attacks, one as recently as a couple of months ago. He had been back at his ranch, though, and seemed to be in reasonably good health in recent weeks.
And I was a kid watching that, and I thought, well, this is really terrible. There's nothing they could do. And here I am standing here, and I could have been standing here actually in 1982 even, and say there was something that could have been done. It just wasn't developed yet. A big criticism that I often hear from people, and it's just a misinformed criticism, is they think we have a problem with population in this world. And in reality, it's the opposite. In the Western world and Eastern world, in civilized countries, there's a shortage of babies. We're not replacing ourselves adequately. And as a result, it's starting to be alarming. It's alarming right now in China in a big way. They're losing a lot of people. They're not replacing them. But it's also occurring in Europe, in the United States to a big extent. We're just not producing enough kids. Wall Street Journal reported on the fact that the fertility rate, the reproductive rates are plummeting. And as a result, there is no problem with a population growth that's going to overwhelm the world, at least in the cultured countries around the world. There still are population growths in South America and Africa, but they're not occurring in countries where, well, that's where we are. We'd like to see more babies being born so they can then use their skills and talents to keep us all alive and functioning. So the multi-billionaires who have the money to do a lot more than they could, they do die. This one lived to 86, worth $31 billion. And he donated a lot of money to scientific research, not aging research that I could tell. But he was a very generous individual with his money, but he died with a heck of a lot of it, and he did die, and someone else now has it. And that's unfortunate. And I'm going to conclude with a slide about Bernie Marcus. And I can personally say I did a TV program with him in April 2020. We had to do it via Zoom. And he was very enthusiastic about supporting aging research. He wanted to get together with me. April 2020, pretty much the peak of the COVID epidemic when lots of people were dying. So we couldn't get together. And net worth, $7.4 billion. He was extremely generous, by the way, donated $2 billion to charities and made it clear he donated the rest of it when he died to charity. I mean, he was an extremely generous individual. But here's the interesting, ironic aspect of him dying on November 5th. And again, we don't talk politics in this church, but the politician that he worshiped, that he funded, that was more important to him than I think almost anything else, he never got to see that particular election. He happened to die on the day of the election, of the guy who he liked, who he supported. And I use that as an analogy. You wonder, should I really go to the trouble of eating healthier, taking an extra step or two to live longer? Well, in this case, had he maybe been able to take an extra step to live an extra day or week, he would have enjoyed it. He said, well, all that money I poured in there and all that enthusiastic support, I won, but he didn't. He died before he could even know it. It's unfortunate. He was a heck of a nice guy, by the way, and I think he would have actually been more involved with aging research had COVID not isolated him and isolated me, and it just resulted in us not being able to talk together. So I don't criticize him as much as I do other billionaires who really don't put money into research. He did put money into some good research. It's unfortunate he didn't live a little bit longer. So if there is time for any questions, I'll be happy to answer them.
We have time, and I bet there's about 2 or 3 questions here, too. And who's got a question for Bill? All right, here we go, back here, John. You drove all the way from Melbourne through a parking lot to get here. I think it was got to be 5 or 6 hours. So, John, you go first tonight.
Ran the gauntlet on I-95 and survived. Anyway, Bill, I was wondering, speaking of Trump, I assume, what are the potential implications of an RFK appointment for the age reversal community?
I can tell you what's going on in the circles that I associate with. And there are multitudes of groups forming right now, hoping to just change, let's put it a nice way, just amend the way new drugs are researched and approved in the United States. They're looking to accelerate the science, the research, and the availability of new medications to save lives. So it's good news in that respect from what we're trying to accomplish. We don't like regulatory barriers slowing progress because we know of people we care for, and they're dying. And we think that they can change the rules, so to speak, in a way that we can accelerate the pace of research in a way that will gain access to age reversal therapies sooner. That's what I'm seeing. My email box is pretty much flooded with people starting groups. They're allying with other people who feel the same way. We hope to see positive change.
2 questions. The first one, how many hours do you sleep and do you ever nap?
Sleep is a challenge for me, and last night I got probably a good 8-9 hours, but that doesn't normally happen. What I will do, though, is if I wake up, I may do a couple hours worth of work, and then I will try to get back to sleep. I know how critical sleep is, and when we put sleep in that house of optimal health as something important, easy to say, not necessarily as easy to do, whereas controlling your blood pressure is easy to do if you make an effort. So I work as hard as I can, and then I do try to get the sleep in that I should, because I know it's life-shortening if you fail to get that good 7 to 9 hours.
And then just a second question. You mentioned that you were unable to get together with that fellow, I think the Home Depot fellow, but yet Zoom and other virtual ways are ways to connect. So I was wondering, you use those virtual ways to connect with people? Because if you couldn't connect in person, I feel like it's unfortunate that you didn't connect more.
Yeah, back then we had a TV show, and we were interviewing people like Bernie Marcus, a lot of high-end people, but COVID struck, so we had to do it during Zoom. But he and I struck up really a nice conversation, and he had undergone some stem cell therapies. Most of the wealthy people I run into are traveling to other countries. We just don't know if stem cell therapies work at this stage. We like exosomes, we like young plasma, we like the gene therapy, OSK or genes. We just don't know if stem cells are a way to really convey super longevity. We hope they do, but we just don't know yet.
Hi, Dr. James Joseph. I practice in Hollywood. Actually, I've seen you at the Red Conference, so it's kind of cool to see you. The question was, and I actually missed it, it was at the bottom of the slide, and I thought that you said that earlier this year, that they combined plasma and the OSK transcription factors.
No, this is a theory. What they did is they took young plasma and they spiked it with a huge number of exosomes. To put it in perspective, when you do an umbilical cord plasma infusion, which some people do, including me, you get a couple hundred exosomes, a couple 100 million exosomes. They used the equivalent of about 4.7 trillion exosomes spiked into the young plasma to reverse aging in the most meaningful way we've probably ever seen. And some people have theorized that they were able to get exosomes encoded with the OSK Yamanaka factors, and it was both the young plasma plus those exosome-rich factors with OSK to maybe induce the remarkable age reversal demonstrated, which I've shown before at the church and at RadFest. So we don't know yet, but they did say they're going to give us that to test in monkeys, and we want to do that.
You said encoded or combined, or?
Yeah, well, what you have to do, just so everyone understands, you just imagine you have these genes, the OSK genes, well, you've got to deliver them inside of cells. And the classical way of doing that is you embed those genes into a virus, an innocuous virus, and then you infect the person with that virus. The virus infects the cells and releases the OSK into the DNA to reverse the aging process. And what we're working on now, since we don't like viruses, are lipid nanoparticles that will also carry the OSK and deliver them into cells, release them into the DNA, and make us young again. That's our objective. So that's a speculation, but just so people understand, when I learned that they were embedding OSK genes into viruses being really tiny, and they're able to put even tinier genes into them and deliver them into cells, it makes you think we're much further ahead, we being the scientific community, than what the people recognize, what the public recognizes is trivial compared to what's really going on in the research lab. And the big delays are transitioning all this good science into older people. We have to test it in mice, monkeys, and people. We'd like to test it in people immediately, but that would not be safe or prudent.
We have one more question, Bill, over here with David.
Yeah, hi, Bill. Dave Feldman from Pompano Beach. This just occurred to me after listening to Mr. Csoka, but I heard you in previous presentations talk about getting the FDA to define aging as a disease. And he was just saying recently in his presentation that he doesn't really consider aging a disease. So would you like to comment on that? Are we still?
Yeah, I will. I think what he said is correct. However, aging is that underlying cause of all these diseases. And some of the groups that are forming right now to amend how the FDA works, that is one of their goals, is to define aging as a disease so that the FDA can approve treatments for aging before that aging causes the diseases that the treatments are approved for. So it's really, I think, just a matter of semantics in many respects and how we view it. We 100% believe aging is a disease that if we cure it, that all those other problems don't manifest. But you could argue it the other way if you want to.
Ladies and gentlemen, Bill Faloon. Thank you, Bill.
Very good. Very good.
Bill will be around to be able to meet with you to answer any questions that you may have through the evening. And I'd like to thank you again, Bill. Appreciate that. And I appreciate this job over here that I have as officiator. What is an officiator anyway? I like that. Boy, an officiator is sort of like a minister in a church that is not a Christian church. It's not a church of cryonics, but it's a church for all people that want to live an unlimited lifespan. I'm a cryonicist. There's many of us here. And next month is our Remembrance of the Resurrectable ceremony, which we have and have had for now 11 years next month. Remembrance of the Resurrectables is something that Julia knows nothing about. And I'd love to tell you all about that, Julia. And so we have a great menu tonight. So this is our Thanksgiving. Obviously, we do have turkey. We also have salmon. Chef Alina and her crew are getting about ready to do that. So I hope that you'll join us now for our lovely Thanksgiving dinner and see us again in December.